Avogadro's law is usually a little bit different from the other laws that we have seen regarding gases, in the sense that now we are changing the amount of gas in a substance. In other words, that number of moles, the small n that we have seen before, is now going to be part of our equation. Aside from that, Avogadro's law is actually very intuitive, and it states that if you want your pressure and your temperature to be constant, to not change, then if you add more moles, more amount of your substance, you have to increase the volume. That's pretty much what the equation states. Volume and number of moles are directly proportional to one another, and we end up with volume over number of moles equals a constant. We have that under an initial set of conditions and a final set of conditions, just like our previous equations. And this right here is what we call Avogadro's law. Relates the volume by the number of moles. Now, one consequence of Avogadro's law is actually very interesting, and it's not very intuitive. It's what we call the standard temperature and pressure conditions, or STP conditions. Now, under STP conditions, something very interesting happens. First, let me tell you what STP conditions are. Standard temperature is 0 degrees Celsius, or 273 Kelvin, and a pressure of 1 atmosphere. Whenever you have these two conditions, then any gas, it doesn't matter which gas it is, if you grab 1 mole of that gas will occupy exactly 22.4 liters. And that amount is what we call the standard molar volume. So we now have a conversion factor under standard temperature and pressure conditions, and we have this consequence, which is not something that was expected by anyone. Let me show you this example just to show you how counterintuitive and unique the STP conditions are. Let's say that we have helium. Helium is the second smallest gas element, actually in the periodic table, element number 2. And 1 mole of helium contains 6.02 times 10 to the 23 particles, and there are 4 grams in that 1 mole of helium. If you look at nitrogen, for instance, nitrogen is made up of 2 atoms of nitrogen, and 1 mole of that nitrogen occupies 28 grams. As you can see, a very big difference in the mass of both elements, or both samples, yet 1 mole of them under STP conditions occupy exactly the same volume, 22.4 liters. Now, because we have STP as a conversion factor, we can calculate volume and moles with one another using that STP conversion factor. So, for instance, here we're looking to see how many moles we have in 2 liters of nitrogen under standard temperature and pressure. Standard temperature and pressure, we're going to be using it as a conversion in the sense that 1 mole occupies 22.4 liters. So that's our conversion factor right there, and our initial quantity. Once you have these two things, you can treat it just like you would any other conversion type problem. We select let's say the nomenclature or the way that we set it up according to our convenience. We're looking for moles, so we want moles on the numerator. Once we decided on that, we have our initial quantity, our conversion. As you can see, liters gets cancelled with liters, and we are left with moles of nitrogen. Combining all of the gas laws that we saw, we end up with a very powerful, very versatile equation known as the ideal gas law. This one relates, as you can see, the pressure, the volume, the amount or number of moles, and the temperature. And there is one constant that we have been seeing throughout the entire chapter. We now are going to call this the ideal gas constant, or the universal gas constant, however you want to see it. That constant is going to take on different values, and the values that it takes really depends on the units that we're using to measure. In other words, we're going to be representing that constant depending on context. Let's say if I'm using liters, atmospheres, Kelvin, mole, then this is the value that I want. If instead of atmospheres I'm dealing with millimeters of mercury, then this is the one that I'm using. That makes our lives a little bit easier because we won't be having to do a lot of conversions between different volumes and pressures, at least not always. Sometimes we're going to have to, but not always. We just pick the gas constant that suits our needs, that matches the constants that we have, or the units that we have. Let's try applying the ideal gas law. Here, for instance, we want to figure out how many moles of gas, in other words, we're looking for that N, right, moles, are contained in a typical human breath that takes in half a liter of air at 1 atmosphere under your typical physiological temperature of 37 degrees Celsius. Now, whenever you're dealing with this type of problem, it's very important that your temperature cannot remain in Celsius. It has to change to Kelvin. So that would be my first step towards solving this problem. But let's first look, or now that we know that, let's look at everything else. We have atmospheres, that's pressure. We have moles as our unknown. We have liters, that's volume. And the gas constant, which we can just go ahead and grab it from our definitions. So no, as you can see, we have all these variables. That means that there's only one equation that we have used so far that has all of those variables, that you can actually use them, and that is the ideal gas law. That's how you choose which of the several equations you're going to be using in any specific problem. Once we do that, we change our Celsius to Kelvin, which is by adding 273 to our Celsius. We pick the gas constant that has the correct units. In our case, we wanted liters and we wanted atmospheres, so we're picking this one. And then it's just a matter of plug and play. We solve for our in other words, divide by gas constant and temperature on both sides. This is the expression. Once we solve it in that form, we obtain our number of moles. That's pretty much it. As you can see, it's relatively simple to use, it's straightforward, but it does require that we take a step back, read through the problem, and look at what do we have and what do we need. One more, and I promise this is the last of the equations regarding gases, is the Dalton's law of partial pressures. Because we have an ideal gas system, if there are two types of gases in any container, then we have to assume that they're not interacting. So the pressure that gas 1 exerts on the system is totally independent of the pressure exerted by gas 2. So when we're measuring pressure, we have to add them all together, literally just add them. So the total pressure of a system is going to be the sum of the pressure of all of the components in the system. That's literally it. We grab all of the pressures, we add them together, and that gets us the total pressure of a system. Let's see how that works out. Here we have a sample of exhaled air, contains 4 different gases with their respective partial pressures. Right? We have nitrogen, oxygen, carbon dioxide, and water vapor. And we want to figure out what is the total pressure of the system. Because we're dealing with ideal gases, remember back when we talked about the kinetic molecular theory of gases, we have to assume that none of these gases interact with each other. So the total pressure is nothing more than the addition of all of the pressures for all of the different components. So we just grab each one, we add them together, and that's it. And that would be the total pressure, 761 millimeters of mercury. And that's it for pressures in this chapter. In our next videos, we're going to be looking at liquids and solids.